Welcome to Plutus IAS, and today we are covering Cram Chelate Model. So from the previous videos you have got the idea that we are covering reagents. Now the Cram Chelate Model is mostly used for the reduction of carbonyls to predict the stereochemistry of the hydride attack in case of use of chelating reagents, for example, that contains metal center that are capable of chelation, for example Zn2 plus, Ce3 plus, Mn2 plus, okay, titanium 4 plus, these kinds of metal which are able to chelate around the carbonyl center. Now apart from this, from our junior classes we already know that Cram Chelate model suggests that the hydride or the deuteride ion, which is from any hydride transfer reagent like NaBH4 or NaBD4, always attack from the less hindered side. Similar is the case with ZnBH4 whole twice and other reagents. But what happens as soon as we switch to different reagents? So in this case, we have a different approach than our usual Cram model that we already know. So first, for example, let's say for the condition. Condition number one that states that there should be on alpha carbon, there should be there should be a polarizable group. A polarizable group. And the polarizable groups are your Nr2, OR, OH, etc. Such kind of groups that we have. Second case arises that the reagent that you should be using, reagents like Zn2 plus that contains metal center, Mn2 plus, cerium 3 plus, and other transition metals, and they are capable of chelation. They are capable of chelation, while Li plus, Na plus, and K plus do not chelate. Do not chelate. So, for example, if I take this particular compound and I add, let's say, OR group here, and let's say some another group R dash here, and let's say add CHC right here for the ease of it, and hydrogen here. So for the case of hydride attack, the options are, as per Cram Chelate model, first I'll convert the molecule in Cram's model like this, where I'll have R dash, and I'm assuming this as, let's say, tertiary butyl group. Tertiary butyl group, which will be our bulky reagent. I'm adding it right here, and then we have hydrogen right here, while here will be OR, and the R group is attached here, which is directly attached to the carbon center. Now in this case, if you see, for a normal scenario, the H minus can only attack from that side which has a less steric hindrance. So clearly it is the case between the hydrogen and OR case. Okay, so in this case, wherever the H minus is attacked, it will have opposite geometry of the OR case. But as soon as I introduce a chelating ligand, chelating metal center, let's such as Zn2 plus, the Zn2 plus interacts with these polarizable groups and withdraws their electron density, which makes the attack of H minus not from the below of the molecule but on the same side as the R, where the carbonyl will take the electron, and this H minus can easily attack the electrophilic carbon right here. So after the reaction, I can see that I can have the possibilities of two attacks. One which exists when the hydride attacks from above the plane, and second when it attacks below the plane. So the molecule number one would be here, here hydride attacks. So the option is, so the option is I can have alcohol with same stereochemistry like the OR at the wedge H, while hydride attacking from the lowest, from below the plane of the carbonyl. Other case I can have where hydride will be on the wedge while OH will form at the back. Now, as per Cram Chelate's model, if I use NaBH4, now since NaBH4 is not capable of chelation, it will attack the electrophilic carbon from that portion where it gets the least stereochemistry, which is in the opposite direction of the OR. So in this case, this product will be the major and form around 93%, and this will form around 7%, which means the probability of getting product number B where the hydride attack from the same side as the OR group is very low. But as per that means in case of NaBH4, our normal Cram model is applicable. Okay, but as soon as you switch to a reagent which has a metal center which is capable of chelation, the entire scene inverts. In this case, this product will be our major product, and while this will be the minor, and the percentage will, this will be the major, and the percentage moves around, let's goes around 87%, and this goes around somewhat 13%. So in this case we can see that it is a major product. Why? Because the OR and the carbonyl can interact, which favors the attack of hydride ion in the same direction as the OR. So as a rule of thumb, we can always remember, whenever you encounter a metal center which is capable of chelation, in case of carbonyl carbons which contains asymmetric carbon center, the hydride will attack from the most hindered side, or it will follow the stereochemistry of the polarizable group that you have in the compound. And if you are using any reagent which is not capable of chelation like NaBH4, KBH4 or LiAlH4, in such cases you will get this as the major product, and your hydride will have opposite stereochemistry as that of the polarizable group. So I hope this would have helped you clearing your doubts regarding the Cram Chelate model, how it works, what are the conditions necessary for it, and how we can determine what kind of product will be formed in major amount. So I hope this would help you. So in case of any doubts, the comment section is all yours. You can just add your queries and we'll solve it. Apart from that, if you have any suggestion or any topic that you want us to make video, you can just directly add to the comment section and we'll get back to you. And thank you for joining us today.